Okay, welcome everybody to today's webinar. My name is Jill Browning and I'll be the moderator for today's webinar, Sustainable Biological Treatment, Removal of Complex and Harmful Compounds from Mine Water. Before we get into our presentation today, I do have just a couple quick housekeeping slides to go over. You should hopefully be able to hear me speak right now, but I do want to just briefly mention that should you have any difficulties throughout the presentation today, that there are two different ways to connect to the audio. You can use your computer or call in through a phone line. The webinar is being recorded today, so we will be sending out a copy of the recording of the live broadcast probably within 24 to 48 hours of that, so be on the lookout for that. And also, due to the large number of attendees on today's presentation, we have gone ahead and muted everyone's phone lines, but no worries, you can still interact with our speaker. In terms of interacting with today's speaker, you can ask your questions via the questions panel at any time throughout the webinar. And at the end of the presentation, we do have some time set aside for a Q&A session. So please feel free to ask any questions that may come to mind throughout the presentation, and we will try to get through as many of those questions at the end as time allows. Additionally, we have gone ahead and made available our collection of on-demand webinars that we've conducted over the last few years. You can access more than 60 on-demand webinars over at www.veoliawatertech.com. So feel free to go over to that website URL and browse through the variety of different topics to see if any of those may be of interest to you. A PDF participation certificate will be made available to you at the conclusion of the webinar today. You should receive that certificate within about 24 hours or so, so do be on the lookout for that as well. And at the end of today's webinar, you will receive a quick survey requesting your feedback. It should take you no more than 20 to 30 seconds of your time. And for those of you who do complete that survey, you will be entered into a drawing for a chance to win a $25 Amazon gift card. So if you would be so kind to fill out that for us at the end of the presentation today, we do greatly appreciate that. Okay, so now before we hop into the main part of our presentation today, if you are not familiar with Veolia Water Technologies, we are a leading water and wastewater technology provider, and we offer our clients a variety of different solutions, from engineering and procurement of advanced water treatment solutions to advanced and robust water treatment technologies, including a line of standardized equipment. We also offer a full range of services, including mobile water treatment solutions for both processed water and wastewater. And last but not least, a comprehensive line of chemicals. So to learn more, feel free to, again, check us out over on the website, www.veoliawatertech.com. Okay, so now I would like to introduce our speaker for today's presentation. Josiane Dallaire is a process engineer with Veolia Water Technologies and is based in Canada. She obtained her degree in chemical engineering at l'École Polytechnique de Montréal. She also holds a graduate degree in environmental management from the University of Sherbrooke. She uses her skills and experience in water treatment by designing complex chains for industrial effluents, water from contaminated sites, and processed water for heavy industry with the purpose of achieving ever more stringent environmental objectives. This allows her to combine her passions for the environment, water chemistry, and processes. And with that, I would like to now turn it over to Josiane to talk with us a little bit more about biological treatment. Welcome, Josiane.
Thank you, Jill. So today I will talk about biological treatment, specifically for the mining market, but please be aware that it can also be applicable in various industries such as oil and gas, pulp and paper, food and bev, municipal, or others. So regarding the agenda, we will explain why biological treatment, talk about toxicity removal, nitrogen removal, and go through a little case study, and finally conclude this webinar. So why do we want to use biological treatment? So the biological treatment is based on the fact that the pollution is actually food for microorganisms. So usually it will oxidize or reduce the pollution of interest using specialized microorganisms called biofilm. The main advantages are that it will enhance the natural degradation of the pollution. It requires low maintenance because you have low mechanical equipment, and it requires low chemical. The considerations of the design is that you need to take into account if you have any toxic compound in the water that could disturb the biological activity. The bacteria will require appropriate nutrients to support its activity, not only the nutrients from the pollution, but other. It's sensible to sudden variations of temperature and loading. The start can be long, and seeding may need to be redone after a severe toxic shock event. There are several types of biological treatment. The most common being the activated sludge, where the biomass is in suspension in the water. These are the ones that we usually see in municipal application. However, this presentation will cover the fixed film biomass in a moving bed biofilm reactor, or also called MBBR, where the biomass grows on carriers called media. So this process will rely on mixing to control the biomass in the system. Densification is a popular topic nowadays. The MBBR is a means of densification of the microorganism community into protected surfaces. It is like a safe space condo for bacteria in order to increase the population in smaller volume. So this allows to have better tolerance on isolated toxicity events. It can tolerate also high hydraulic flow variation and TSS in the effluent. So the MBBR consists of a tank filled with media, aeration grid connected to a compressor to diffuse air, or ensure mixing for aerobic reactor, or mechanical mixers for anaxic aerobic reactors. It also contains sieves to keep the media within the MBBR and instruments for monitoring. The required volume will be defined by the pollution load, so flow times concentration and temperature. Typically, the minimum temperature of operation will dictate the design. So the large protected surface gives really robustness to the biofilm in case of sudden increase of toxic compound. In mining application, we will use mostly painted steel field-erected tanks for big flow, big load, or we can also use FRP for low load application. It is also an auto-cleaning process since the mixing with air or mechanical mixing will allow contact of the carriers and will promote the sloughing of the biomass. Depending on the water characterization and criterion, the reactors can be installed in series to optimize the kinetics of each tank, and each tank will grow specialized microorganism population for the pollution to be treated. This helps to avoid competition between the bugs and optimize the design. Also, to be noted, the biofilm can operate at low temperature down to 1 degree C, especially with mature biomass. As it is aging, the biomass is more and more efficient. The performance won't be the same after 3 months versus after 12 months. The kinetics will get better over time. So mature biomass will be more resistant and resilient. This is one of the main features of a fixed film bioreactor. Nature is well made, as life can occur at extreme conditions. This is why MBBRs can be installed for exotic application. The specific wildlife can grow at high temperature. We have application that can go up to 40, 42 degrees C to treat the pollution, while different wildlife will populate a reactor at lower temperature. This is the same for pH. At low pH, we can develop bacteria that will reduce or oxidize sulfate, for example. As the population is different, the kinetic is different too, and the volumes need to be calculated accordingly. Also, MBBR can work in saline environment or in the high scaling potential application. So special attention needs to be done for these applications, and Veolia has developed the Media Z that is not affected by scaling. The Media Z will work even if there are scaling conditions where the typical media will sink. When we are facing new application, we will like typically to test the equipment to make sure that this is a good application for the process. It takes about 4 to 6 months typically, and it can help also to establish a strategy to speed up the startup. We don't usually use bench scale tests for kinetic design. We will go for pilot scale testing. So in that way, we can better appreciate the impact of water variability. So the biological treatment, MBBR, will shine when you have limited footprint, when you need to integrate it in complex solutions, when you expect to have high flow variations, or you need to manage load variation. You can do that in using heating because the kinetic will be faster at high temperature, or using recirculation if you have low load. You can also go with phasing, again using heating, or using different filling rate as the loading is increasing over time. What does it need to drive? You need to have the water access year-round, or you can also schedule downtime for extended periods of time with progressive startup. You need to get rid of every inhibitors that could affect the treatment, or do an adequate design, not too small but not too big, because you don't want the bugs to be starved. They need to be fed. And you need also to add some nutrients or reagents such as the alkali for pH control, carbon source if you need to go to denitrification, ammonia, phosphorus source also to keep the C and P ratio optimal. To give a more robustness to the system, we usually add a heating system. That can be done not only to prevent freezing, but also it helps if you have sudden load increase to recover from a toxic shock. It will help also to speeding up seeding phase and increase the MBBR capacity. We usually also use a heat exchanger for heat recovery and OPEX reduction. Toxicity. Toxicity is a complex concept and can be driven by many factors. Also, the tested species won't be sensitive to the same pollutant, so the solution needs to be global. In the next slide, I will present few elements that can bring toxicity and that can be treated using MBBR system. So in a mining site, especially for gold and silver, they will use cyanide in their liquefaction process for gold and silver concentration. Of course, cyanide is highly toxic and needs to be treated. So usually the mining will have a detoxification treatment based on chemical oxidation, such as INCO or other oxidation process. So this will transfer the cyanide into cyanate. The cyanide can also be treated biologically through aerobic biological treatment at neutral pH. And again, the end product is still the cyanide. It needs also to be noted that when you convert the cyanide into cyanide, and if you discharge that into a pond, yes, you will have natural degradation in the pond because of the UV lights. But the cyanide will still be converted into ammonia, which can be also toxic, and to nitrate. Nature always takes the shorter path that requires the least energy. Cyanide species request less energy to degrade the ammonia. It's like candies to bugs. They will prefer cyanide species over ammonia. So that's why you better want to remove any cyanide species prior to go into a nitrification process. So the thiocyanates is a byproduct from the reaction of cyanide and pyrite. If your ore is containing pyrite within, you will produce some thiocyanates. And this, again, will inhibit your nitrification process and will degrade into ammonia if you want to degrade it naturally with the light. So the thiocyanate is easily biodegradable in the MBBR. The oxidation is really quick and the acclimatization is really, really rapid, and it will produce some ammonia and sulfate at the end. So the cyanides is similar to the thiocyanates. The only thing is that the hydrolysis is slower. The kinetics will increase over time. So it will take a couple of months to grow the appropriate microorganism to treat for cyanides. So it's normal to see that the treatment is slower. The end product again is ammonia and bicarbonates. Biological treatment can also treat for thiosalts, which can be produced if you do process sulfide ores or if you have a acid mine drainage issue. And thiosalts is really difficult to treat. It cannot be easily precipitated, but it's highly biodegradable at lower pH through an anaerobic biological treatment. However, you really need to be careful. If the water contains some calcium, you may have a scaling issue, so you really need to do the design accordingly. Organic acid like citric acid or ascorbic acid are not really harmful for the aquatic life. However, if you have citric acid or ascorbic acid, mainly coming from the CIP cleaning in membrane technology, you want to get rid of these chemical because it really can affect the chemical precipitation. It's a chelatant, so it will affect coagulation, any chemical precipitation. It's easily biodegradable within an aerobic system. Again, bacteria works in neutral condition. So in doing that, if you have MBBR to degrade these organic acids, you are buying you peace of mind if you have physicochemical treatment on the site. Now, what about nitrogen removal? So ammonia is really toxic for mainly trout on its unionized form. So you really need to get rid of that. It will damage the gills, the tissues. It will produce hemorrhaging on the trout. You need to treat for nitrogen. For the nitrate, there is usually no issue with nitrate. There is no criterion on nitrate. However, it can cause eutrophication and reduce the dissolved oxygen of your receiving body. So some of the client or some of the regulator ask to treat for nitrate. So the main mechanism for ammonia removal, for nitrification, you want to treat ammonia and it will be converted first in nitrite and after in nitrate. It's mechanism that is actually work in parallel. However, note that it's more difficult to treat ammonia from nitrate than nitrate from nitrate. So when you do the startup or when you have an upset condition, it's not unusual to see that you will have some nitrite spikes that will go down after some days when the microorganism will develop to treat the nitrate. So the end product of the ammonia oxidation, it's nitrite and also acidification. So you produce hydrogen. To get rid of that, you need to dose for some alkali in the system. And also regarding the nutrient, you need to put some phosphorus in that kind of process. However, there is no need to put any carbon because these are autotrophic bacteria, and autotrophic bacteria, they will synthesize their own food with the inorganic carbon present in the nature. As for the nitrate, this is an anoxic biological treatment. So the microorganism will use the oxygen from the pollution as oxygen. So we don't need to inject free oxygen. We need to ensure the mixing through mechanical mixing. The end products are nitrogen and CO2 gas. So it's really, you really do a complete oxidation of the pollution. However, you need to add some organic carbon as energy source because it's heterotrophic bacteria and it cannot synthesize its own food as for the ammonia removal system. Also, you need to note that anoxic biological treatment can also get rid of selenium and also sulfate. It's the same mechanism. They will use the oxygen from the elements as an oxygen source. So the bacteria will first want to treat for nitrate or to eat the nitrate after the selenate and after the sulfate. It will depend on the ORP and the carbon dosage in the water. So now we will go through a case study. So this is a Canadian, This is a Canadian gold mine. It's a large gold mine in northern Quebec. So at first we built the plant in 2013 and it was only to remove metals, so zinc and copper and arsenic mainly. But after the startup, they saw that the effluent became toxic. So the metals only was not enough to remove the toxicity. So the mine got ordered, of course, to stop the toxicity, and they needed to come with a solution to treat that. So at first, the first stage to design a biological treatment, an MBBR, is to define what is the load of pollutants to be treated. For this specific project, it was not that easy because the plant was running in a loop for several years, so it was really difficult to define the load. It was really not obvious how much nitrogen was needed to be removed. For this project, the nitrification was not required because it was really the nitrification that was getting rid of the toxic component. The design temperature was 8 degrees C and the water was heated with a heater. And also the material selection was done as a corrosion protection system because the water was containing high chloride concentration. So in the square, it was the original plant, and the MBBR are all the tanks at the left. So at first, we had only the MBBR for nitrification and cyanide compound oxidation. But we kept some room for future expansion for if we need to have additional nitrification or if the nitrification was required on the plant. So this is some picture of the installation. So it's actually the starter ring that was anchored to the foundations. And again, this is during the installation. So the way that is installed is that they begin with the top ring of the tank and they attached it to a hydraulic screw jack system. And the sidewall sheets are added from the ground level until the ring is complete. The ring is then raised with the jacks and the next ring down is added. So this is the way they are building the thing. So this is some results after 2 years, a bit more of 2 years of operation. So when we analyze the loading, we really see that the treated load increased with time. and it continues to increase for months. Also, you need to note that the system was actually designed to treat 450 kilograms per day of nitrogen, but actually it was able to treat for 130% of the design. So this is really this show how robust can be that kind of system. The average load was 50% of the design. This show that when you do a design on a biological system, it's not advisable to put too much security factor when you do the design. You don't want to have a too big system, and we know that it will be better with time. So this is really the conclusion of the loading. Regarding the temperature, the first temperature was in operation at 8 degrees C because below that they were having like poor results. So they were using the heating system extensively. However, the subsequent winters, they were operating at 4 degrees C, and they would have be able to operate below 4 degrees C, but they were actually limiting to by the freezing. The pipe was not heat traced, and they were limiting by freezing. So that's why the temperature was limited at 4 degrees C for this specific site. So regarding nitrogen species, we can see that the nitrates, it took like 3 months to go below 5 ppm, and again it's because the ammonia to the nitrate to nitrate reaction is slower than ammonia to nitrite, so that's why you see that you have a peak of nitrite. The water was not toxic anymore after 3 months of operation. And you can see also that from time to time, you can have some peaks, some spikes in nitrogen species when the water quality change, or you have something. We are dealing with living bugs, so of course it's not always steady states. So finally, why we want to go with MBBR? Because biological treatment is actually a way to enhance the natural degradation of the pollution. It's natural. It's just we want to give like the bugs the best conditions for the pollution that you have. It's possible. It's a possible solution for many sources of toxicity coming from nitrogen, cyanide species, COD sources, also selenium and sulfate. And you need to note that each application is unique, and the design need to be done for each application, because the best solution is not always the same for one application to the other. Thank you. So I will take Jill will take the lead as for now.
Yeah, thank you so much, Josiane, for that very informative presentation here. With that, I'm going to kick off the Q&A session that we have right now. Just a reminder, if you do have any questions, feel free to type those over into the questions panel. And with that, we will kick it off. So first question here is, do you have any references of upscale plants operating at between 1 to 3 degrees Celsius?
Yeah, sure. We don't have a mining application right now, but we have in municipal application a system called Lagoon Guard that is put after a lagoon to polish for nitrogen, ammonia removal. So we know that it can operate way below 3 degrees, like close to freezing. Yes.
Great. Another question that came in is, let's see, do you, oh, apologize, I've got a bunch of questions popping in and I'm having an issue with my questions panel, so I am going to try this here. So do you have a way to measure parameters in real time to, one, optimize the treatment process, and then two, know how successful the treatment is? And with that, for example, for the nitrates and sulfates.
Yes, of course. We usually will monitor the system for dissolved oxygen pH. If you have an anoxic system, it will be more the ORP, but you can also have specialized analyzers such as nitrate, nitrite, ammonia. But most of our clients, what they like to do is take samples and do their analysis in laboratory. So this is really a good way also to monitor the process. Yeah.
Great, thank you. Another question that came in is, what is the best method for residual mining reagents and their degradation products?
What is the best method for, I'm sorry, I didn't get the question.
Yeah, for residual mining reagents and their degradation products.
To me, again, biological treatment is really the best way because it's natural. You're just enhancing the nature. So it's really, to me, you give it the best condition to enhance the biodegradation. So MBBR is really a good way to do that.
Okay, another question that came in here is, what are your thoughts on the operating temperature limitations of the feed water and the optimal range?
So honestly, this is really, I believe it's an OPEX CAPEX study. So you can design the temperature as you want. You can use whatever like design temperature, but at some point you don't want to spend money on heating. So you want to use a temperature not too high to make sure, but to make sure to optimize the OPEX.
Great. A question on media type. How do you select the media type, and how does high suspended solids affect MBBR's performance?
So typically, we are using two types of media. So one is called K5, it's like a honeycomb, and the other one is Media Z, which is like a Pringles. And whenever you don't have any scaling potential of the water, we will go with the K5. The only thing is if you have scaling potential, like regarding for example, calcite or gypsum or something like that, the problem is that the calcite will go on the media and will sink the media. So in that specific application, we have the Z media that won't sink if you have scaling potential in the water. And regarding the TSS will just like pass through the MBBR, so it won't affect the system.
Got a question, just a little bit more clarification, or if you don't mind going back and just talking a little bit more and just re-explaining some of the results in the load for the case study, if you don't mind. There was a question on that.
Yeah. So what's the question? I didn't.
Just if you could just kind of re-explain that one slide.
Okay.
Talking about the load.
Okay, so what we can see is that the loading is increasing, like the treated loading increase with the time. So the juvenile microorganism won't be able to treat as much as like load or pollution than a mature biofilm. So as you seeding the system, as it grows, it will get like more performant, and it will be able to, like, if I can say, eat more pollution in a certain amount of time.
Okay. A question specific to biofilms. Just if you could explain, or if you've got some different examples of different biofilms that could be used.
So the biofilms, we don't use biofilms. So the biofilms will naturally grow depending on the conditions. So it's like bacteria or fungus or any microorganism present in the nature that will just fix they will be fixed, they will fix themselves, if I can say it that way, on the media. So we don't seed the microfilm. Okay, so it's really developed as per the conditions.
A question on discussing maybe the pros and cons of MBBR versus IFAS technology or EFAS.
No, I'm not. I cannot comment on that.
Okay.
Maybe Miriam, are you there? I don't know if you have some.
Yes, I'm there. I must say we haven't seen a lot of IFAS. We will come back to you. We'll come back to the question.
Yeah, and I do know, yeah, we use IFAS a lot within municipal. So for the person that asked that question, we can follow up directly with you and talk a little bit more about that one-on-one. Another question here is, what could inhibit biological activity and that required pre-treatment?
So mostly metals like copper. So copper, it's well known as a biocide. So you don't want to have any copper in this system. So what we do is we had some precipitation up front. And since you are in presence of ammonia or cyanide compound, you want to break it. It will be complex with those species. So you will need to break this complex. Also, if you have organic matters or cyanide, you will do the design accordingly, just to make sure that there is no competition between the microorganisms. And also, if you have scaling potential and you prefer use the K5 media beside the media Z, you will need to have a softening system up front.
Okay, there's another question that just came in, and I'm not sure exactly, but I will ask it and maybe they can give some more clarification. If not, where can the treated water be used specifically?
Usually, the treated water will be discharged into the environment, usually, but you can use it in your process if you want. And this is a good way actually to make processed water, because you don't want to have buildup of ammonia in your system. It's not a good. It will become really toxic, and it can be also healthy for the workers. So you can use this water as processed water. This can be done. Yeah.
Great. Well, I think, again, I apologize because I'm having an issue with my question panel that's popping up today, but I believe that we've answered all of the questions that have come in. If for some reason we have missed one, I do apologize for that, and we will follow up directly with you as well. And with that, that will conclude our webinar for today. We do kindly thank you for all joining us. And again, if you would be so kind to take that short survey at the conclusion today, we are greatly appreciative of that. And if you are the lucky winner of that Amazon gift card, the $25 Amazon gift card, we will reach out to you directly. So with that, that concludes our webinar, and we thank you all, and thank you, Josiane.
Thank you.